Good evening, everyone. My name is Alexandru. I'm a PhD student at the University Polytechnic of Bucharest. And in the following minutes, I will try and give a presentation on the topic of stiffness, so optimization to a modified greedy algorithm. This study is part of a project we are currently working on. It's called Ripe for Tech. You can visit its website, and along with our Austrian partners, we are trying to create heterogeneous 3D printed structures based on epoxy polyamine resins that are composed of soft and hard microscale domains. In this presentation, I will make a small introduction, talk about the problem description, methods we used, some results, and of course a few conclusions at the end. As it has been the case in many engineering discoveries, inspiration can come from different interesting materials found in nature, which can exhibit high defect tolerance due to their composite microstructure and insensitivity to flaws in their microstructure. We have materials that can combine complementary properties such as brittleness and ductility, or stiffness and softness. For example, nacre, which is here on the slide. It's made up of 95% calcite materials and only 5% biopolymer protein, and has a toughness 3,000 times higher than normal brittle minerals alone. What we are trying to do is replicate nature's composite structure with numerical modeling. As a problem description, we have a 2D domain. We consider the 2D periodic domain as shown in figure 2a, for which we know that it's composed of two materials. In this case, the materials are 50% soft material and 50% hard, but the ratio can be variable. We consider that we know the Young modulus. In this case, we have as input 1,000 for the soft material and 10 times that for the hard material. And the objective is to find a material distribution that ensures extreme effective properties. For this purpose, we identify a representative cell. You can see it in figure 2b. And to further simplify the results, we analyzed only a quarter of it due to symmetry conditions. Figure 2d shows the boundary conditions we applied to our cell. You can see that it's made up of 16 finite elements, and we constrain the x equals 0 line and the y equals 0, and coupled the other two lines. So we could apply forces or introduce displacements. For a linear elastic analysis, the stress distribution for each finite element cell is variable if we do not consider a reduced integration element or stress mediation of a whole element. But to further simplify the results, we consider that the stress is constant on each element. As output, we I showed here on the slide the main property in our analysis, which is the effective stiffness of the quarter plate we analyzed on the x direction and y direction. You can see the formulation on the slide. And because we are trying to create a structure that is isotropic, we are trying to maximize these two properties. So our problem is a multi-objective one. And because of that, we needed to formulate some objective functions. And we have here 3 formulations we considered and we tested. We'll see how they reacted in the further slides. In order to get a sense if our algorithms are accurate enough, we needed to create a brute force algorithm so we could see if the results from our greedy algorithm is the accurate one. We will talk about it in detail in the second presentation. For now, we need to know that using a brute force algorithm, we can get all the possible material distributions and the value of the objective function for each distribution in order to see if our results from the greedy algorithm is in fact maximum from the whole one. Here we build a Pareto diagram to show the EX and EY values for each configuration. On the dashed line here are all the results that have X, Y, and AX equal. And if we look closer in the area where the dashed line intersects the Pareto frontier, which is here, we can see that the best solutions that ensures perfect isotropic behavior are these 4 on the left, which are on this line. Also, there are 2 more here that are not perfectly isotropic, but under a 5% difference. About the greedy algorithm, it's an, as the name says, it's an algorithm that takes as input an initial random population of soft and stiff materials. From this initial configuration, the objective function is evaluated, and in order to decide the best solution for the next step. One element at a time is then replaced by the opposite material. For instance, if the element at hand is a soft material, such as the case in the first picture here, it will be switched to a stiff material. Then the program, because the volume fraction is the same, 50% soft material, 50% hard material, it needs to change another element into a soft one. So it searches for all the combinations possible and changes the best one in a hard, soft material. It logs all the results and keeps the best possible combinations for each one. It evaluates its current objective function value, and if its value is higher than the one from the previous iteration, it takes these iterations as the new one. If it's lower, the program prompts the output and exits. So we said that choosing an objective function for the algorithm is a very important part of the optimization process, because it dictates which next step is the best to take for as an argument. We tried 3 different formulations and tested how they influence the results, and we have the results here. As we can see, we started from the same initial distribution, and we can see that the first one and the third objective functions run 3 iterations. They didn't reach the same configuration, but they reached a pretty good value, while the second objective functions couldn't find a value that would suit our needs. As a result, here are presented what we obtain with the greedy algorithm and the first formulation of the objective function. If we analyze the results, we can definitely say that this formulation of the objective function is not the best, because it rarely reaches the known maximum value, which I didn't specify here, but it's somewhere around 3,900 for the objective function. So you see it's quite low compared to the global maximum we got from the brute force analysis. Now we can see also that the final distribution obtained is very much dependent on the initial distribution, because we ran 3 tests and neither of them provided the same result. If we look at the Pareto diagram, we can see that these 3 configurations I showed you are not even close to the Pareto barrier here. They are over here somewhere, here. So we can say that this formulation is not recommended to solve this kind of problems. Another formulation, which is on the slide, presented better results, because we got even higher to the global maximum. We got from the brute force analysis. We can see here the effective stiffness on X direction, on Y direction, and the evolution of the objective function. And these solutions were pretty close to the Pareto frontier we showed earlier. This is another run. We also see the evolution of the objective function. And this is a run we tried, and we saw that not even this objective function is not perfect, because as you can see, the initial configuration did not improve very much in terms of effective stiffness on X and Y direction. This tells us that this model needs further improvement to be validated to a bigger scale and use it without brute force approach. For a conclusion, we can say that for a specific material combination of structure, we can have different and more than one material distribution depending on our objective function. The formulation of this objective function is the biggest point of interest, to say, in this model. And although we proved that the third formulation gives better results than the first one, the algorithm doesn't always reach global maximum. And we need to improve or search for another algorithm that can get close to that Pareto frontier. We'll talk about another algorithm in the second presentation. For references, we can check these 4 sources, and that was my presentation. Thank you for your attention.